Next, we look at studying a general polynomial congruence. In particular, I want to look at the technique of lifting solutions. So what do I mean by that? Okay, so we start with the congruence mod p, where p is a prime, and I want to lift the solution to this congruence to a solution of the congruence mod p to the n power. Okay, so that's the primary goal of this section. We're going to have two types of solutions we talk about, singular solutions and non-singular solutions, and they'll have a different type of behavior when we do the lifting. Then finally, we'll use the Chinese remainder theorem to solve a congruence with a general modulus and determine the total number of solutions of a general polynomial congruence. So let's start by looking at a congruence mod p squared, where p is a prime. So let f of x be any polynomial over z, and consider f of x congruent to 0 mod p squared. Now note that any integer solution of this congruence must already be a solution mod p, because this is saying p squared divides f of x, and so in particular p would have to divide f of x. So we have to start with a solution mod p. So let x1 be a solution of the mod p congruence right here. I'll give that equation number 1. And we're going to attempt to lift this to a solution mod p squared. So what do I mean by that? I want to find another integer x2, which is the same value as x1 mod p, so it continues to be a solution mod p, and has the stronger requirement that it's a solution mod p squared. Okay, so since x2 is congruent to x1, it's of the form x1 plus t times p for some integer t. Then I do a Taylor expansion. So f of x1 plus tp is f of x1 plus f prime of x1 times t times p plus f double prime of x1 over 2 factorial times tp squared. And then in general you'll have terms where you take the kth derivative evaluated at x1 and divide by k factorial, and you go all the way down and stop when you get the dth derivative of x1 over d factorial times tp to the d power, where d is the degree of the polynomial. And why does the Taylor expansion stop at degree d? After all, in calculus we learned that a Taylor expansion is an infinite series. But if it's a polynomial of degree d, what happens after you've calculated the dth derivative? Well, as soon as you get to the d plus 1 derivative, this is identically 0. Every time you do a derivative, you knock the degree down, and therefore the series actually stops at degree d here. So note, the polynomial in t on the left-hand side right here is clearly a polynomial with integer coefficients. So f started with integer coefficients. You're just plugging in an integer x1 plus t times p, and so that has integer coefficients. And therefore, although it looks like I've written down a bunch of fractions with these terms right here, these are really whole numbers we're talking about. This is a polynomial with integer coefficients. And every term after the first two, you'll see a p squared. So there's a p squared. The next term would have a p cubed, p to the 4th power, which means all of those terms vanish mod p squared. And so we're just left with the first two terms of the Taylor expansion, f of x1 plus f prime of x1, when we turn this equation into a congruence mod p squared. That is, so this is x2 right here, f of x2 is congruent to f of x1 plus f prime x1 tp mod p squared. And we're trying to solve this congruence f of x2 congruent to 0 mod p squared. And so we have the following. F of x2 is congruent to 0, is equivalent to solving this congruence right here. That is, f of x1 is congruent to negative f prime times tp mod p squared. Now note, p is a divisor of everything in this equation. By assumption, p is a divisor of f of x1. And so this congruence is equivalent, dividing everything by p, to saying that f prime of x1 times t is congruent to minus f of x1 over p. So I just divide everything through by p, and I move this term over to the left-hand side. And this is what we call the lifting congruence. And it's just a linear congruence in the variable t. This is just an AT congruent to B mod P. The three options for solving the lifting congruence. So again, I've written down the lifting congruence right here. Option 1. Suppose P is not a divisor of f prime of x1. Therefore, this integer has a multiplicative inverse mod P. And we can solve uniquely for t, and we get a unique solution x2 mod p squared, or a unique lifting of x1 to a solution mod p squared. Option 2. If p divides f prime, but p squared doesn't divide f of x1, well, that would mean that p is not a divisor of f of x1 over p. So the left-hand side is 0 mod p, and the right-hand side is non-zero. You would have an inconsistent congruence in 3. And so there's no solution. There's no solution t, and thus no lifting of x1. Option 3, if p divides the first derivative, and p squared does divide f of x1, and so p does divide f of x1 over p, then both sides of 3 are 0, and hence you can let t be any value. And thus we get p distinct solutions of congruence 3, and thus p distinct liftings of x1 to a solution mod p squared. Okay, now the game continues as we go to higher moduli, p cubed, p to the 4th power, and you just do one lifting at a time. So far I've gone from mod p to mod p squared, then you go from p squared to p cubed, and suppose you've done this inductively, and so we've constructed a sequence of integers x1 through xn, such that xi is always congruent to xi minus 1 mod p to the I, and f of xi is a solution mod p to the I power. So we've done it inductively, and now we want to continue to the next power of p. So let's go to the mod p to the n plus 1 power. To continue means mod p to the n plus 1. And so I want to find some integer such that xn plus 1 is congruent to xn mod p to the n, so it's of this form. And when you plug it into the polynomial, it comes out to be 0 mod p to the n plus 1. So f of xn plus p to the nt is 0 mod p to the n plus 1. Well, we do the same thing we just did. We do a Taylor expansion, and all of the higher order terms cancel out, and we just come up with this congruence. F of xn plus f prime times p to the nt, so that's the first order expansion of this polynomial right here, should be congruent to 0 mod p to the n plus 1. Now p to the n is a divisor of f of xn by the assumption that xn is a solution mod p to the n. And so dividing everything through by p to the n here, so you just divide everything through, you get this congruence. F prime of xn times t should be congruent to minus f of xn over p to the n mod p. And this is again a linear congruence called the lifting congruence. And you can go one step further by observing that since xn is congruent to x1 mod p, that was coming from this condition right here, f prime, which is some polynomial, evaluated at xn, is congruent to f prime evaluated at x1. So every step of the process, you can replace f prime of xn with f prime of x1, the original integer we started with. And so we arrive at the following lifting congruence. The left-hand side is always going to have x1. You can replace the xn by x1 times t is congruent to minus f of xn over p to the n mod p. And so again, we've got the three options. If p is not a divisor of f prime of x1, we get a unique solution, and so a unique lifting. If p divides f prime and p to the n plus 1 does not divide f of xn, then you would have 0 congruent to a non-zero number. It's inconsistent, and so there's no lifting. That's option 2. And then finally, option 3 is when both sides of the equation are 0. So p is a divisor of the derivative. P to the n plus 1 divides f of xn. And thus you would have p distinct solutions. T can be any integer value, and you get p distinct liftings to a congruence mod p to the n plus 1 power. Notice in this process we have a special case where p doesn't divide the derivative, and so we're going to call these non-singular solutions. So a solution of the mod p congruence is called non-singular if p is not a divisor of the first derivative, and it's called singular if p divides the first derivative. Non-singular solutions are very friendly because they always allow unique liftings at every step of the game. And so we get the following theorem. If x1 is a non-singular solution of the mod p congruence, then for any positive integer n, there is a unique integer xn mod p to the n of the congruence f of x congruent to 0 mod p to the n, such that xn is the same value as x1 mod p. And the proof is straightforward. So at each step in the lifting process, there is a unique lifting. If x1 is a non-singular solution. So that means there exists a unique x2, so that exclamation mark means unique, in the integers with x2 congruent to x1 mod p and f of x2 congruent to 0 mod p squared. And then there'd be a unique x3 with x3 congruent to x2, which is congruent to x1, and f of x3 congruent to 0 mod p cubed, and so on. A formal proof would just use induction. All right, let's do an example to see how this works. Take the polynomial f of x to be x cubed plus x squared plus 23. The derivative is 3x squared plus 2x. So I start with a mod p congruence. In this case it's mod 5. And I'll just solve this by trial and error. Plug in 0, that fails. 1 works. 2 works. 3 fails. And 4 fails. Incidentally, when you plug in 4, you should just plug in -1 to make the arithmetic easier. So we have two solutions, mod 5, x equals 1 or 2 mod 5. Okay, case 1. Let's suppose we take the value 1 and try to lift it. So I take x1 equal to 1, and I want to solve for some x that's congruent mod 5, so of the form 1 plus 5t, and I need to solve for t. So we have to write down what the lifting congruence looks like. So I calculate the first derivative at 1. So f prime is 3x squared plus 2x. Plug in 1 and you get 0 mod p, or 0 mod 5. And so 1 is a singular solution. Then I calculate f of 1 divided by 5. That'll be the right-hand side of the lifting congruence. So f of 1 is 25. Divided by 5, we get 5. And 5 is 0. So in the lifting congruence, both sides are 0. So t is arbitrary. And thus, we get 5 distinct liftings to a mod p squared congruence. So x can be 1, 6, 11, 16, or 21 mod 5 squared. So this is mod 5 squared. The next step, we want to lift these to solutions mod 5 cubed. Okay, and well, the idea in what we just discussed was to take each one individually and try lifting it from mod 5 squared to mod 5 cubed. I'm going to do all of them at once by just letting x2 be of this form, where t is 0, 1 through 4. So I'll just let x2 be of the form 1 plus 5t, where t is one of these numbers. And I want to find the lifting congruence. So we've already calculated f prime of x1. That's on the left-hand side. You never need to recalculate that. So this was 0 mod 5. This is a singular solution we're dealing with here. So what I have to calculate for the right-hand side is f of x2 over 25. So this is going to be on the right-hand side of the lifting congruence. And I just calculate it. So I take f of 1 plus 5t, plug it into the polynomial, and after doing a little bit of arithmetic and simplification, I'll let you bother with that, it just boils down to 4t squared plus t plus 1. And so we see that f of x2 over 25 is 0 mod 5 if and only if t is equal to 3. So you're just solving 4t squared plus t plus 1 congruent to 0 mod 5, which is and I think it's probably as easy in any way just to do trial and error. Yeah. I was trying to be clever, maybe complete the square or something, but you only have 5 numbers to work with, and just test. 0 fails, 1 fails, 2 fails, 3 works, -1 fails. I'm not doing that in my head. You can take extra time to calculate it. So just 3 is the winner there. So this is the only value that permits a lifting when t is 3. When you plug in t equals 3, you get x2 is 16. Thus, only x2 equals 16 will permit a lifting, and both sides of the lifting congruence would be 0, so you get 5 distinct liftings. You take 16 and you add multiples of 25 to it, so 41, 66, 91, and 116, and those would be the distinct values mod 125. For the other solution, x1 equaling 2, we calculate its derivative. So I look at f prime of 2, And I have to go back to the polynomial x cubed plus x squared plus 23, and f prime is 3x squared plus 2x. So 3 times 2 squared plus 2 times 2 is 12, plus 4 is 16, which is non-zero mod 5. So you get a non-singular solution, so there's a unique lifting, and after solving the lifting congruence, and I'll let you carry out this calculation, you derive that x2 is congruent to 17 mod 25, and that x3 is congruent to 42 mod 125. So there's two separate liftings I have to do to solve the lifting congruence at each stage there. Now there's a nice way of diagramming the solutions, mod these various powers of 5. So we started with the solutions mod 5, and we found that there were two solutions. So those are these two solutions. We had x equaling 1 or x equaling 2. So we've got 1 and we had 2. Then we went to mod 5 squared. And let's identify which one is which. So this is the singular solution, and this is a non-singular solution. The non-singular solution always has a unique lifting. So 2 proceeded to go to 17 and then to 42. And that's at the mod 5 cubed level. Whereas 1, how did it proceed? It went to 16 at first. It went 1, 6, 11, 16, and 21. So it lifts up here. So you got 1, 6, 11, 16, and 21. So you have 5 distinct liftings, and then only one of those values continued to mod 5 cubed, and that was 16. That's what we were studying right here. Only this one will lift, and that one lifts because a singular solution, you'll have 5 liftings of it. 16, 41, 66, 25, 91, 25, 116. Now what if we went to mod 5 to the 4th power? You might think this pattern continues. Well, for non-singular solutions it does. You will get a unique value here. I didn't carry out these calculations. For singular values, anything can happen. It really depends on the polynomial. And in this case, you might think, well, maybe it's just 91 that will permit a lifting. Well, no, something strange happens. Turns out that every one of these values can be lifted. So you get 5 solutions for every one of them, and so altogether we've got 26 solutions here. So number of solutions. The mod 5 you had 1, we had 6 solutions here, still having 6, and then all of these split and we get 26 distinct solutions mod 5 to the 4th. Finally, suppose we have a general modulus m, and I want to solve the congruence f of x congruent to 0 mod m. Well, all I do is factor the modulus as a product of prime powers, p1 to the e1 times pk to the ek, right here, and use the Chinese remainder theorem. So we have a theorem that'll say x is a solution of this congruence, f of x congruent to 0 mod m, if and only if x satisfies the system of congruences mod the different prime powers. So that's a system of k congruences right here. And so if I want to count the number of solutions, let's let capital N of m denote the number of solutions mod m, and capital N of pi to the ei, the number of solutions mod pi to the ei. Then the number of solutions mod m is the product of the numbers of solutions mod each of the prime powers. And this is a straightforward theorem. So part 1, all we're saying is the following. So f of x congruent to 0 mod m is equivalent to saying that m is a divisor of f of x. And that's equivalent to saying that each of the prime powers is a divisor of f of x. And that's equivalent to saying that f of x is congruent to 0 mod pi to the ei. So that's going on there. And in part 2, we say, well, let's suppose x sub I is a solution of the congruence f of x congruent to 0 mod pi to the ei, where I is going from 1 to k. All right, so you suppose that for each prime power, you've come up with an integer solution. So x1 mod p1 to the e1, x2 for mod p2 to the e2, and so on. Well, by the Chinese remainder theorem, there exists a unique x that is congruent to xi. Well, let's write it like this. There is a unique x mod m with x congruent to x sub I mod pi to the ei, where I goes from 1 to k. And why is that? Because these are distinct prime powers, so they are pairwise relatively prime. Well then, for that value of x, f of x is therefore congruent to f of xi mod pi to the ei. That's just substitution. X is congruent to xi, so f of x is congruent to f of xi. But f of xi by assumption is 0. Bingo. So anytime you give me a k-tuple of solutions of these congruences modulo the different prime powers, I come up with a unique value of x mod m satisfying this condition here, which is equivalent to saying that f of x is congruent to 0 mod m. Thus, if you're trying to count how many solutions there are mod m, you just count how many solutions there are for each of the prime powers. So how many choices are there for the mod p1 to the e1 congruence, and I compare that with any solution to the mod p2 to the e2, and I compare that with any solution to the mod p3 to the e3, and so on, and thus the total number of solutions is just the product of the number of solutions mod the prime powers.